Guys, so we are going to continue from the topic which I hope we have completed in the live class, right? So that this is a continuation of rotational motion. So you can take this video as a second part or the second video session of rotational motion. So the topic which we are going to take today is torque, right? Torque, and its representation is tau. It is also called moment of force, or it is called turning of force. There is a force which can cause turning or rotational motion, right? So see, in the linear motion, what process the force does, that is what is to be done, or that is what that torque does in the case of rotatory motion. So I can say that in linear motion, force, right, its same part or counterpart is torque in the case of rotatory motion. That is, suppose we are going to an example of a nut, right? I am using a spanner, right, to to loosen it up or to remove this nut, right? So what you want to do, you want to remove it, so you will turn the spanner like this, right? That is, you're going to apply a force. I'm going to take an example that this direction is for loosening and this is direction for tightening, right? So I will be moving the spanner in this downward direction to loosen it up. So you are going to apply a force, or you are going to or an amount of turning is happening, right? And that amount of turning is known as torque, right? And that amount of turning is done by application of force in a downward direction, right? So this, how much turning can happen, right, or how much torque is happening. I'm extremely sorry, let me keep that mobile in silent, right? How much turning or how much rotatory motion is happening is depending upon three factors, which is how much force you are going to apply, right, then where you are going to apply, right, and in which angle you are applying, right? So this basically on three criteria, the torque or the rotatory motion of an object depends, right? That is, first let's talk about force, right? It's very easy. When you increase the amount of force, the same case of the spanner, you are applying a large force, obviously the turning will be maximum, right? So I will say the torque is high, right? Similarly, you have learned about torque in your lower class. Torque you would have learned as what? Application of force into perpendicular distance from the applied point, right? That will, we come to that later on, right? So this much is clear. So the force and dependency of torque with it, that is when the application of force increases, the rotatory motion or the torque increases, right? Now let us take another example. The same, or not, let's take the same example. This is the nut. I'm using a spanner to remove that nut, right? Let's say I'm going to apply the force here, so that this becomes the distance of the what? This can be called as the pivot, right? Or the distance of the nut from the force. Let's not go for the pivoting section, I will take that later on. Let's say this is a nut, right? So I'm going to apply force at this end of the spanner. Similarly, in order to remove the same nut, let's say I'm going to apply force here, right? So that now the distance of the force and the nut has now reduced, which is going to produce a maximum movement, right? Well, that is, I can say where your application or where you can see maximum torque, you will see torque higher in this section. In this arc, there is a technical term which is called a moment arm. Moment arm, right? So when moment arm increases, torque increases, right? This and all we can explain by using examples, so that is a better way of understanding. Now the third criteria is in which angle we are going applying the application of the force, right? See, suppose same example, let us take the same example of nut and the spanner, right? Suppose I'm applying a force in this direction, right? That is here, right? Let us say I'm applying the force from the below, so I can extend it, right? So force is a vector, so I can extend it. Let's say it is making an angle theta with the horizontal. So obviously I can make it into two components of f cos theta and f sin theta. Yes, I can, right? So you can see this component, which is F cos theta, it is only pulling the spanner in this direction. It is not causing any rotatory motion, right? Rotatory motion causing force is called as torque. So F cos theta is not causing any rotatory motion, hence it is not causing any torque. So which component is of force, right, is going to cause a rotatory motion? That is F sin theta. Or I can say the perpendicular component of the force, right? Perpendicular component of the force is the what which is causing the rotatory motion, or I can say is causing the torque. This much clear? So you got 3 points, right? So torque depends upon R, that is the distance of the applied force from the point from where you are going to measure. Usually it is called a pivoting point. Here the pivoting point is usually, or the example which you have taken is our nut. Example, I'm just talking about this one. Suppose this is rod. Let's say this edge, this end is pivoted. Pivoted means this object can move around in this way or in this way. Right? This is fixed. This end is not. So this point is called pivot. So in this pivoting condition, right? So let us say I'm applying a force in this direction. So how much force increases, right? That much will be the increase in the torque. And R, that is called the moment arm, is the distance of the applied force from the pivot, or from where I'm going to calculate the torque. Clear? So R is this distance. This much clear? And it is depending upon perpendicular force, right? So F sin theta, or I can say torque is equal to R cross F, right? So cross product etc. I have taken in the earlier chapters. So I hope you remember how to take the cross product. This much clear, right? Right? Clear. So let us take another example, guys. I want to make you guys understand the logic. So let us take two axes like this. Let's say a body is like this, right? So that the pivoting is here. So the object can rotate like this, here in this direction or in this direction. Clear? Okay. So let us say, okay, let us say we are going to apply, say, a force in this direction, right? Such that it is making an angle theta in this direction. So this becomes R, right? The distance of the applied force from the pivot, that is R, right? Clear? So that is, you are having F in this direction, means obviously you can make two components. This is F cos theta and this components become F sin theta, right? Now F cos theta is passing through the axis of rotation. This is the axis of rotation, right? This is going to rotate in this direction or in this direction. So this is the pivoting point, right? So this point is the, or this line which we have drawn is the axis of rotation. So I can say F cos theta, we have already told about it, that F cos theta in this scenario is not going to cause any torque. So what is the specialty of F cos theta? F cos theta is passing through the axis of rotation, right? So torque due to F cos theta is what? 0, right? That is, since T or the F cos theta component, it is actually along R, right? These are all very important scenarios, guys. Listen. Or I can say F cos theta, or the component of force along the moment of arm, or moment arm, right, is not causing any torque. Clear? The force along the what? R, which is actually moment arm, doesn't cause any torque. Clear? Right? So what causes torque? This, that is the component of force, right, which is not along the moment of arm is what causes torque. Clear? Right. So earlier we wrote the torque, that's why we wrote it as R cross F, right? So you can write RF sin theta, and usually you write an n cap also. Remember in the earlier classes I taught you what is n cap. N cap is the what unit vector which gives the direction of what it gives the direction of torque. Now that is another I hope you have understood the section, right? So the direction of cross product, I believe you have got understood it during the live class. So I'm taking another example of the same spanner and nut case, guys, right? This is the nut. Okay, so you are applying a force here. So this is the distance r from the nut. So I'm going to extend this r vector, let's say like this. So how can I take the direction of torque? Keep that in mind, guys. You are always taking the angle from r to f, right? You are taking the hand from r to f, so it has to be from tip to tip, right? This, if I suppose I go from this direction to this one, so tip of r is looking at the end of f. No, so this is not the way. So what we can do, we can extend f like this, right? Now the tip to tip movement, so I can move from r to f in this direction. So when you turn keep your fingers, all the fingers in the direction of r and bend it towards f, you will feel that the thumb is into the plane, right? That is, your entire finger is moving in this direction, clockwise direction, right? So there is a short form, guys. So clockwise direction if the movement of torque, right? The torque is obviously into. The thumb gives the direction of what? Torque. The thumb is into the plane, right? So thumb is into the plane and the rotation is in what? Clockwise direction, right? So let us take always the clockwise direction as negative. Take always the clockwise direction as negative. It will be helping out doing the problems. Okay, so again r, then f, tip to tip movement. So r direction, keep your fingers, bend it towards f, you will feel the thumb is into the plane, so torque is into the plane, and your fingers are indicating the direction from here to here, that is the rotation, right, is in clockwise direction. Clockwise direction, take it as negative. So obviously out to, then another case, if it is out to, then it is anti-clockwise rotation. So anti-clockwise rotation, please take that rotation as positive. This is a conventional method which you can use for doing problems. This much clear? Right. So suppose we are given another question. This is a disc like this, this pivoted at here, right? So the rotation can be in this direction or in this direction, right? This much clear? So let us say a force F is applied of 10 Newton here, right? You're asked what is the torque. Let's say this radius is 2 meter, right? Or this distance. It is very easy. Torque is equal to R cross F, right? This, you need not find the direction. You know that obviously the disc is going to move in this direction. Huh? So this direction is anti-clockwise. So you can write R cross F. What is 2 into 10? It is 20 Newton meter. That is a unit of torque. And it is positive in nature. Rotation is in what? Anti-clockwise direction, right? No, sorry, in which direction it is closing? It is this one, no? This is clockwise direction, so it is minus 20 Newton meter. I'm extremely sorry, it is clockwise, so minus 20 Newton meter, right? Easy, right? Now similarly, let us take another example of rod. Let's say it is pivoted at this point, and we are applying a 10 Newton in this direction. Let's say it is making 37 degree in this direction. So obviously we can make it into two components, 10 cos 37 and this is 10 sin 37, right? Out of this 10 cos 37 is a long r, right? This is r distance. Let's say that r, I'm giving it as 1 meter. So force is applied at 1 meter away from the pivoted point, right? Since this 10 cos 37 degree, right, is along the what? Along the axis of rotation, I can say. Along the point through the axis of rotation or along the moment arm, this is not causing any torque. So torque is caused by 37 degree. So 10 sin 37 degree, that is a force, into perpendicular distance becomes this r, which is 1 meter, right? So the calculation you will get as 6 Newton meter, right? Sin 37 degrees 3 by 5. Okay, and direction, sorry I didn't talk about it. So which will be the direction, guys? So this is your F, this is your R, right? So this is F, this is R. So rotate from here to here. So this is anti-clockwise direction rotation, and the torque is into, right? So it is positive. Clear? Right? So similarly, I'm taking a lot of examples so that you understand the logic of it, right? Suppose there is a block. Initially it was here, right, Bob, and it moved. Let's say this is 1 kilogram. It moved in this position. You are asked what is the torque of all forces which are acting on 1 kilogram about x. About x means that is the pivoted point, right? So let's say it has been displaced by an angle 30 degree, right? So simple. So there will be a tension along here, right? And what and all other force will be there? 1g, weight will be here, right? Right. So torque due to tension, that is torque due to tension, is 0. Why? See, I'm going to extend the tension like this. Okay, let's talk about tension only here. What will be R? This will be R, right? The force applied point is this one, and this is the pivoted point. So this is R, right? And I am extending R means tension and R is on the same line, right? Even if they are in the opposite direction. So T and R in the same line. So this tension, which is a force, doesn't cause any torque. Clear? This much clear? Now, so then we can talk about the gravitation. This is this guy. Torque due to 1g. This angle 30 means this angle of 30 degree, right? This is R vector and this becomes force, right? So this weight also is having this 1g sine 30 degree and this is 1g cos 30 degree. Now 1g cos 30 degrees along R, so it is not going to cause any torque, right? So 1g sine 30 degree is going to cause your what? Torque. Torque is equal to this 1g sine 30 degree, sorry, not theta, it's 30 now, sine 30 degree into the radius. What is R? Not radius, the distance, perpendicular distance, which is what? 1, right? So you will get 5 Newton meter as the answer. G I have taken it as 10, right? And what is the direction, guys? See, this guy is pulling here, right? This becomes a force direction. This is R, force R. So R cross F is from here to here. So this direction is what? It is what? Clockwise direction. Clockwise direction means negative torque. Clear? Right? So negative, and you can say it is into the plane. Easy to understand. Clear? Oh shit. Sorry. Did I say a bad word? Sorry. So this this is another disc. Okay, this is pivoted at this point, right? Let's say there are 20 Newton here and another force, let's say 10 Newton hat in here, right? So, and this distance is 2 meter. Obviously this distance is also 2 meter, right? You are asked what is the net torque. So net torque will be sum of the torque due to 20 Newton plus sum of the torque of 10 Newton. Now what is the nature of these 2 Newtons? This force is here in this direction, and obviously radius outwards, right? This will be the R direction. So R cross F in this direction, right? R cross F, this is in what? Clockwise direction. So torque due to 20 Newton is negative in nature. This much clear, right? Right. Negative, or I can say it is clockwise, or it is into. Torque is into, rotatory motion is anti-clockwise. Sorry, I am repeating anti-clockwise. Into is the torque and the rotation is clockwise direction here, right? Moving from this point to this point, it is clockwise direction. So negative in nature. That is rotation negative. I would write negative to in order to sum, right? While you sum, I will make you understand why I am taking it as negative. So it is clockwise. The torque is what? Force into perpendicular distance, that is 20 into, what is the perpendicular distance, guys? 2. So it is 40, right? So, and I will write it as 40 Newton meter, right? Now what is torque due to 10 Newton, right? So this will become the R cross F, this direction. So this is in which direction? It is an anti-clockwise, so it will be positive. Force into distance, that is 10, and what is the distance? 2. 10 into 2 is 20 Newton meter, right? So when you are asked what is the net torque, it is sum of these two guys. It is minus 40 plus 20 is minus 20 Newton meter. So net torque is minus 20 Newton meter. And minus indicates means the net torque will be causing a clockwise direction rotatory motion, and negative means the torque is into the plane. Clear? Right? Similarly, if you given a vectorial question, that is if you are given force is acting, which is 2i plus 3j minus k cap. I'm not writing the k cap, okay, write it here. And it is acting at a point 1, 2, 2. So 1, 2, 2 is the pivoted point, guys, right? And find the moment of force about the point 0, 1, 2, 3. So oh no, then you are okay, I'll tell you this. Write the question. I'm just reciting the question. There is a force this much is acting at a point 1, 2, 2. Find the moment of force about the point 0, 1, 3. So you are asked the moment, sorry, not moment of force, you are asked the torque. Actually, moment of force is another term for torque. So you are asked what is the torque about this point. So that means there is a point here, let's say that is O. That point is 0, 1, 3. At a distance, say 1, 2, 2, a force is going to act. Right? This force can be below force or whatsoever. A force is going to act which is having magnitude like this. So you're asked what is the torque here. This much clear? So you have to find the distance r vector here. What will be r vector here? This position difference, right? So r vector is equal to what? 1 minus 0 is 1, right? So it is I cap. Then 2 minus 1 is 1, that is j cap. Then 2 minus 3 is minus 1, that is k cap. So you got r, you got f. So you just have to do what? In order to find torque, it is r cross f, right? So you will make a determinant form. So I, that is minus j, and then k. Then it is 1, 1, minus 1. Then for force it is 2, 3, minus 1. So how would you do the cross product? First keep these guys constant, right? Then I, right? I into 1 minus minus 1 is minus 1, minus minus 1 by 3, right? Minus 1 into 3, right? So what is it? So plus 3, that is it becomes 2, right? So this factor will be how much? Minus 1 plus, okay, this will become 2, right? Sorry. So I cap into 2, right? Now minus j, then keep this guys constant. 1 minus 1 minus 1, minus minus 2, so it becomes plus 2. So minus 1 plus 2 is 1. So I will write it as minus j itself, plus k. I've taken it a lot, guys, that's why I'm taking it fast. 1 into 3, 3, 3 minus 2 is plus 1. So remove that one. So you will get the value of torque like this. This is the torque. If you are asked what is the magnitude of torque, that is root of 2 squared plus 1 squared plus k squared. So it will be root 6. Clear? It's not that tough, guys, right? So one thing is for sure, when force is acting parallel, right? If any force, this is r, right? Any force which is along the moment of arm, that is along r, or any force which is parallel to arm is not going to produce any torque. The force has to be perpendicular, will be maximum, but any components which is perpendicular, if suppose the force is this direction, so the force component which is perpendicular will be causing the rotatory motion. Clear? So this much clear. So remember, the torque is equal to 0 when force is parallel to the r. F is passing along the axis of rotation, right? See, remember, this was the axis of rotation, right? Suppose this is a force and this becomes r. So this force is along the moment of r. It doesn't cause any torque. This force is also passing through this axis of rotation, right? So this force is not causing any torque. Or I can say when fast or the force is passing through the pivoted point, it doesn't cause any torque. Write it down, guys. I'm not going to specially write it on the board so that you guys can copy it. Write us, take another scenario, guys. Hope you will understand. So this is, see guys, what and all I'm now taking now, it is part of your curriculum, right? Explicitly only few sentences has been written in your textbook, but in order to understand the logic, obviously this and all section should be very much understood before going to the numerical section or whatsoever. So a force is applied like this, guys, and I'm telling you that torque, I wrote it as Tina, sorry, torque is not equal to 0. That means there is torque here, but this torque is not causing the turning. It is not causing any turning. That is example here. There is a disc here, it is pivoted in this point, a force is applied here, this is an R, obviously this will be the R. I've just extended, it's a vector quantity, right? So I'm telling you there is torque, but this torque is not causing a rotation. Now you wonder why, how? See, very important, guys. Now see, here this is R and this is F, so you will take R cross F in this direction, right? So when you take that R cross F, you will see that the torque is towards your face, right? This is a disc, right? So the torque, if I'm drawing from this point, if I'm drawing, the torque will be in this direction. Keep your fingers, guys, right? It will be towards your face. See, the R is at the edge here, right? Clear? It is moving out. The torque is outside, right? Now what is the axis of rotation here? Right? So the axis of rotation, let's say this one. This is the axis of rotation, right? Now this torque is having no component along the axis of rotation. So if I take the torque's component like this, right? There is no component which is along the axis of rotation, right? That's why the body is not going to rotate. Keep this in mind. So torque can be a non-zero factor, right? Even if there is torque, you can never say that it can rotate. Torque may be there which is not causing rotation, right? There are some torques which doesn't cause rotation. Keep that in mind. Those torques which are having the components along the axis of rotation will only cause the rotation motion, right? Keep that in mind. Again, this is and all of very smaller points, but reason and assertion type questions, etc., it can be understood. So I will explain with another example. See, suppose there is a disc like this, right? This is a pivoted point, so this will be the axis of rotation. This much clear? Let us say we are going to apply a force here in this direction, so that there is an angle theta here, right? I'm not taking this way, okay? This is not a top view. Just think that the plane, or you are looking in a face like this, right? So that the person who is sitting over this edge will feel that there is an angle theta like this, okay? So let's say there is one component F1 here and there is another component F2 here. This much clear, right? Right. Now F1 and F2 are two components, right? So let us take each components individually and we will talk about their contribution in torque, right? Let us talk about this component F1, right? So I'm going to separately draw F1 here. This is F1, right? And this will be the direction of R, right? This is the pivoted point, right? Now this F1, right? And this is R. So what will you do? R cross F, this direction, right? So always think from the edge. So R cross F1, when you're taking, the thumb will be in upward direction. So that is, you will draw torque in this direction. So the axis of rotation is here, right? So torque is upward along the axis of direction. That means it will cause the rotation in this direction. That is, now the disc will move in this direction. Right? So this torque which is due to F1 is something which is going to cause a rotation. This much clear? Right. Now, yes, there is another component, which one? F2. Right? So I've taken this disc again. This is the axis of rotation here. Right? This is F2. Right? So this was r vector, right? So r vector, r cross f, I have to take this one, right? So keep that in mind, this torque is in this direction, right? Clear? The other one I have taken it at the edge, guys. It is better if you understand, you take it as this f1 as at the edge, then it will be very easy, right? Clear? This f2 and this r is causing a torque in this direction. This much clear now, right? Whereas this torque is not having, right? This torque, if I just say this torque, if I extend draw from this point, I can just drag it here and I kept it here. So this becomes torque here. The same torque I have drawn here. And this is the axis of rotation, right? So that means if this is a paper, if I'm doing the side view, this is torque direction and this is axis of rotation, right? So this torque is perpendicular to the axis of rotation. So this torque is actually what doing? It is pulling the disc outwards. It is not causing any turning effect. So the disc torque, which is perpendicular to the axis of rotation, doesn't cause rotational motion. Clear? So keep this in mind. Very important. Torque which is perpendicular to axis of rotation doesn't cause turning, right? Or I can say torque which doesn't have any components, right? The torque which has no components along the axis of rotation, right, will never cause rotatory motion. Clear? Right? This is very important scenario, guys. Clear? So next we are going for the very important topic of equilibrium. You understood the things which I told now. It is purely theory, guys, but it is very important to understand. So when will be torque becomes zero? When the force is parallel to the momentum, or r, or if force is passing along the axis of rotation, right, or it is passing through the pivot point, right? These three conditions, if it is satisfied, then the torque due to that force F is equal to 0. Similarly, when can I say that torque can exist but doesn't cause any rotation, right? That is a type of torque which is not going to cause any rotation, right? That happens when the torque is perpendicular to the axis of rotation, right? The torque is not equal to 0, but there is no rotation, right? It happens when the torque is perpendicular to the axis of rotation. These 2 points are very important to be understood. Yeah, it is just mentioned as a sentence in your textbook, but it is very important to understand the scenario. Clear? Now, after moving on to the torque, we are going to the next topic, which is angular momentum. Now, angular momentum, its symbol is L, and it is analogous to the linear momentum, which is P. That's why there is a relationship between angular momentum and linear momentum, which is L is equal to R cross P. Right? I hope you remember. See, almost all the parameters you see, there is a relationship. See, V is equal to R omega, right? Or omega cross R, right? Omega cross R. Just like that, you can write this one also, right? So there is a relationship between linear angular momentum and our rotational angular momentum, or I can say it is angular momentum. This much clear? So this is the expression for it. Nothing to more details. Obviously, conservation, etc. I will say. Okay, so R cross P can be written as RP sine theta, right? Again, cross product means you have to suppose this is R direction, this is linear momentum direction, then the direction of angular momentum you take by taking your hand and turning the right hand's fingers towards P from R, right? Then the thumb gives you the direction of L. Clear? Now, see, someone asks you to differentiate this equation. What would you do with respect to time? So you will write it as dl by dt is equal to d by dt into R cross P, right? Let us give this differentiation to both the terms. So I hope you know the product rule of differentiation. If not, remember differentiation of the first term, that is dr by dt, into the second term plus differentiation of the second term into the first term. This is an equation, guys. This is not something which is made by me. It is just mathematics. Differentiating the first term into the second term plus differentiating the second term into the first term. Right? This much clear? Right. Now after this one, now tell me what is dr by dt, that is rate of change of displacement. So I can write it as what? Velocity. So I will write it as velocity vector cross p vector plus dp by dt, that is r cross dp by dt. Right? Now let us keep this one as this one. What is p? P vector is mv, right? P is linear momentum, that is mv, right? Plus r cross dp by dt, right? So you are having v cross mv, that is you are crossing two common terms. What is I cross I? 0. J cross j? 0, right? So when you are multiplying two vectors, common vectors like this, right, the product is 0, cross product, plus, right, r cross dp by, sorry, did I write it as dq? dp by dt. This much clear? So here what was the LHS side? It was dl by dt is equal to r cross dp by dt. Now what is rate of change of momentum? It is force. Alright, so I'm going to write dp by dt as force. Now what is r cross f? You have learned that. What is r cross f? It is your torque. Right? So I got a relationship between angular momentum and torque, which is dl by dt is equal to torque. This much clear? Right? So this gives the relationship between angular momentum and torque. Very important derivation, guys. It is usually in examination straight away the question comes up. Now see guys, now we are always considering a system of particles rather than a single body, right? So if this is a system of particles, right, so the torque can be two types. The torque can be due to the internal force, that is which happens between the particles, and the torque can be due to an external force which acts on the object, right? Right, so I have to find whether dl by dt is equal to torque internal or torque external, or if it is a sum of it. Right, now that is what we are going to find now. So in the consisting of a system of particles, the total angular momentum will be sum of individual angular momentums of each particles till ln, right? So I can write L is equal to sigma I is equal to 1 to n li. This is writing the format, guys. It is mathematics sum of, right, sum of each. So when I put I is equal to 1, this becomes L1. When I write I is equal to 2, it becomes L2. So summing li from first number to nth number, that is the symbol's meaning, right? So I can write L is equal to, what is li, right? L, any angular momentum, is equal to cross product of r distance into what? Linear momentum, right? So I can write sigma I is equal to 1 to n. In place of li, I am going to write ri cross pi, right? Keep here. Now the torque also is for system of particles, right? So we just found a derivation or relationship between torque and the angular momentum, which is torque is equal to dl by dt, right? And then torque is also sum of sum of individual torques, right? So I can write torque is equal to sum of, right, here dl by dt, right? Similarly I can write torque is a sum of individual torques of individual particles. So torque T I can be written as dli by dt. I just suffixed here, there is no suffix, so dl by dt. Here there is I suffix, I just made into, right, then the symbol sigma, right? Now we have already written torque is equal to sigma ri cross fi, Yeah, you know it, right? If you don't know, understand it, right? Now, what will be tau external then? Tau external will be sigma Ri into Ri vector into what type of force it will be? Force external, right? Similarly, what will be tau internal? It will be sigma Ri into force internal. Now, when I consider a system of particles here, each particle which is producing a torque, suppose, or internal force, if it is producing an attraction like this, then there will be a repulsion somewhere else, right? So that in internal section, in a single system of particles, if I consider, the internal force is 0, right? So there is only external torque excess due to the presence of external force. That's why when you write torque is equal to dl by dt, this torque is external torque, not internal. This much clear? This is little bit lengthier process, but I hope you understood, right? So how we did, please review the or just go through the derivation again, you will understand. This is very simple derivation. Clear? Right? Now we are going for the next topic, which is equilibrium of rigid body. Equilibrium of rigid body. Now the major types of equilibrium which you have to learn is static equilibrium. When do you say that a rotatory motion which is happening is said to be in static equilibrium, or rigid body when you say as static equilibrium? When the total force, right, is equal to 0, as well as when the total torque is equal to 0. That is, when do you say total force is 0 means that is force in x direction is also equal to 0, right? That is delta fx is equal to 0, delta fy is equal to 0, and delta the sigma, del sigma fz is equal to 0, right? Similarly, total torque is equal to 0 means sum of torque in x direction is equal to 0, sum of torque in y direction is equal to 0, sum of torque in z direction is also equal to 0, right? So when you consider in a system, right, any particle you take, its individual force and individual torque it experiences is equal to 0, then I would say that object is said to be at equilibrium. Which type of equilibrium? Static equilibrium. There is a case called partial equilibrium also, which is not there in your textbook, but good to know things. Suppose I am going to take here, right? I am going to apply a force F1 here, F2 here, right? Someone asks you whether there is a net force. You will say net force is equal to 0 in the system. Yes. But would this object rotate? Yes. That means the torque is not equal to 0. So this is a partial equilibrium case. Similarly, let's say there is a scenario like this. There is an F1 force here, F2 force here. Someone asks you if there is a net force. Yes, there is a net force of F1 plus F2. And someone asks you whether torque is there. No, it is not going to rotate, so there is no torque. So either one is existing, then that type of equilibrium is known as partial equilibrium. This much clear? Right. Now, in order to understand the scenario, some of the problems are existing. Suppose you have a structure like this and you are having a rod connected like this, right? And there is a tension T1 and there is a tension T2 here. Let's say this bar is of 10 kilogram and there is a small mass kept here which is of 5 kilogram, right? Which is at a distance say 40 centimeter from this end, and this rod is of a length 100 centimeter. This much clear? Right. You are asked at static equilibrium what is the value of T1 and T2. Right. So one major important point you have found is it is in static equilibrium. So what is in static equilibrium? First point, the net force is equal to 0, right, on the rod, right? So that means, see, there is no x direction force, only for a direction forces are existing, right? So you will just deal about that. So when you consider the rod, its own weight of 10 g's downwards, right? Along with it, this 5g is exerting a downward force, so I will write 5g, and upward there is T1 and T2 forces. That is only Fy here, and you have been told all the force in the y direction is equal to 0 because it is in static equilibrium, right? So can't I write T1 plus T2 is equal to 15g, 10 plus 5g. Okay? That is 5, then it becomes 150. I'm substituting g as 10, so it becomes 150 Newton, right? Clear? Now keep this one, we require this equation. Now similarly, there is another scenario or another point when you consider static equilibrium, that is total torque is equal to 0, right? So let us take the same structure, right? Here let's say the center of mass of the rod, let's say it is O, right? That is giving you mg. Rod I have taken this as mg, right? Now the mass is here kept, it is a distance 40 centimeter from the center, right? And there is a tension T2 here and there is a tension T1 here, right? And this mg, this rod entirely is length 100 centimeter, means center of mass will be exactly at its center, right? So this will be 50 centimeter. This much clear? Now that means this small mg, that is of this block is in this direction, means this distance will be 10 centimeter, and this obviously has been 40 centimeter as mentioned in the figure. This much clear? All right. Now because we are going to deal with torque, so force as well as perpendicular distance from the axis of rotation has to be measured. Now about O, right? That means where it is going to rotate, it is going to, I'm going to assume that it is going to be rotating from O. The point from where it is going to rotate, you can assume it, guys, right? Now torque due to 10g, that is due to this guy, right? What it is, I would say it is 0. Why? See, this is a point of rotation and I have taken the force, this one, this point is point of rotation and the force is this direction, so there is no r. If the point of rotation this one, then this distance becomes r, then I can multiply r into f. But here the force is acting on the axis of rotation, that means that force is causing no torque. Clear? Now similarly, torque due to tension 1, right? So this is the tension, this force, and it is at a distance 50 centimeter from the axis of rotation, so I can write T1 into 50. Clear? Now the problem comes whether it is plus or minus. See, this torque is this one direction, and r I can take it as, tell me which direction this is going to rotate. Due to T1 it will be rotating in this direction, that is clockwise direction, right? Clockwise direction rotating, remember it is negative, so I will write it as negative, right? Now torque due to T2, this guy, right? So again from here to here the distance is 50 centimeters, so T2 into 50. This much clear? But this rotation due to T2, the rod will be moving in this direction, right? That is, the rotation is in this direction, so that means it is anti-clockwise, so it is plus. This much clear? Now torque due to the any other force remaining, yes, this guy, the blocks, that is 5g, right? So that is this force into the distance from the axis of rotation, which is 10, so I'll write it as mg, that is 5g into 10. The question is, it is going to move in this direction, means that is clockwise direction, so it is minus. Alright, clear? Now net torque will be this plus this plus this plus this, and that is equal to 0, right? Clear? So that is 0 plus minus 50 T1 plus 50 T2 minus 50g, 10 into 5 is 50g. That is equal to 0. Why? Net torque is equal to 0. From here you can get T2 minus T1 as 10. You already found T1 plus T2 as 150 Newton, right? So you can find T1 and T2 now. T1 you will find it as 70 Newton and T2 you will find it as 80 Newton. Yeah, calculation you guys can do it by yourself. I wanted to make sure that you understand the logic. That's the big thing here. Clear? Right. Now this a common type of question which is asked is ladder type problems, right? So let's move on with the ladder question. This is actually there in your textbook even. So this is a wall, right? You are suppose having a ladder like this, right? Now let's say this is a rough surface, right? See guys, I'm going to give an expression only, numerical sections, number type questions can come up, right? So I'm just giving expressions for it. So let's say the ladder is 2L length, it is angle at theta, right? Let's name this point A, right? Both of them are rough surface, right? Now you are asked, let's say that initially it is at equilibrium, right? So you are asked, anything can be asked. I'm going to give just the expressions, clear? So a person is going to, no, is going to move from here to here, from here to here, any point from, so let's say he's moving from this end. While he moves along this path, at some point the ladder might fall down or slide down. So you are or you sometimes you can be asked how much distance he has to move from this point to this point so that the ladder just starts sliding, right? That might be the question, right? So many things can be asked. I'm just giving the expression, guys. Hope you will understand, right? Clear? So remember, here there is a contact, right? So, and this is a rough surface. So what tendency this part will be having? It will be having a tendency to move down, right? So the friction at this side will be in the opposite direction of motion. Let's say it is FR2, right? Similarly, the sliding of the ladder here will be in this direction. So the friction will be in this direction. That is, let's say it is FR1. This much clear? Now ground is giving a normal reaction here. Let's say it is N1, and this point of contact here is this one. So the normal reaction will be N2 here. This much clear? Right. Now let's say this ladder is having a center of mass located here. So ladder, let's say it is having capital M mass, so its weight will be capital Mg downwards. Now let's say a guy, right, who is going to move downwards, right? So he will be also exerting a weight downwards, that is Mg. This much clear? Right? Right. Let's say this person is moving, has moved by a distance x, so that at that point it starts to slide. This much clear? Now it is said that the entire system is at equilibrium, means I can directly write that F net is equal to 0, right? That means Fx is also equal to 0, Fy is also equal to 0. So sum of Fx, that is all the forces in x direction. What and all are the forces in x direction? N2 as well as Fr1, right? So I can write N2, right, is equal to Fr1. That is the first equation you can write. Similarly, in the case of Fy, that is force in the y direction. What and all are y direction forces? This mg and this mg is there, and there is an N1 in this direction, and there is an Fr2. So I can write N1 plus Fr2, that is upward forces, is equal to downward forces, is equal to small mg plus capital Mg. You got an expression here, right? Don't mug up the equation, guys. Understand the logic. Similarly, you can write net to torque is equal to 0, right, in the static equilibrium, right? So similarly, torque due to individual forces you have to consider. So the problem comes from where I can take the rotation. You can take the rotation from any point along this ladder, that the ladder can rotate while it is sliding. You can take this point as its sliding point, or you can take this one, right? So depending upon, that is experience, right? So take that point from where you can make the calculations very easier. I will take this A point. Do you know why? If I take this point as axis of rotation of the ladder, then I can negate this guy. Which one? N1. Why? N1 is out the axis of rotation, so obviously N1 force is not going to contribute for any torque. Clear? Right? Clear? So I'm going to take the point A as the axis of rotation, right? So from A of perspective, I'm going to reduce the size so that you can understand. So prime A points of perspective, that is, this becomes this point. I'm going to consider only this rod, right, for the case of, okay, let's redraw it. Torque due to our ladder, this guy, right? So he is at a distance of what? How can I consider? Let's redraw that guy. This is mg here, and this is the point A here, right? What will be the perpendicular distance from the axis of rotation? That is our r, right? Torque is equal to r cross F, F is a force which is this mg, and what is r? That is a perpendicular distance of this force from the axis of rotation. So what is the perpendicular distance? This one, right? This is the perpendicular distance. Keep that in mind. Okay, so this r, how can I find? This entire rod or ladder is of length 2l, means this length will be l, right? Because this is center of mass, right? So this r, this angle is theta, means this r is equal to l cos theta, right? So I can write torque due to mg is equal to what? Mg force into r, that is l cos theta. Now this mg is bringing the ladder downwards in this direction, that is, it is a clockwise direction, right? So that means I will put a minus here. Clear? Now what will be torque due to small mg? That is this guy. That is this guy, what he is causing the torque. That is mg into the perpendicular distance, right? So from here to here, remember he is at a distance x from the center of mass, right? So x plus l, from here to here it is l, then from here to here it is x. So this guy is at a distance of l plus x from this point A. So his perpendicular distance will be from here to here. Let me take another color. So his perpendicular distance will be this, right? Clear? And this distance is l plus x. So what will be this? It will be l plus x cos theta, right? So while I write for mg, torque due to mg, small mg, it will be mg l cos theta, and it is also bringing the ladder in clockwise direction, so I will write it as minus mg l cos theta. Now similarly, what is torque due to n2? That is this guy. This is n2, this is n1, sorry. Okay, I've written n1. So this n2, right? So let us make this a little bit larger, right? And when I correspond to point A, this becomes the perpendicular distance from the axis of rotation. This becomes n2, n2. This and all are vectors, right? n2, this one, and this is the perpendicular distance from the axis of rotation, right? So how can I measure this point? How can I measure? This entire length is 2l, right? From here to here, right? And this angle theta means this angle is also theta. So this becomes 2l cos theta, and this will be 2l sin theta. This much clear? So the perpendicular distance of n2 from A becomes what? It is 2l n sin theta, right? So n2 into 2l sin theta. Now whether it is positive or negative, this guy will be causing the rod to move in this direction, right? What is continuing it? It is anti-clockwise direction, right? So I will write it as plus. Clear? Similarly, the torque due to second friction. This guy. See, he is at a perpendicular distance this much, right? So this is entire 2l. So this distance will be 2l cos theta, right? So here I will write what? FR2, force into perpendicular distance, is 2l cos theta. He is also causing a positive or anti-clockwise direction movement, so it is plus. So when you equate for total torque is equal to 0, you just have to add these values and you equate it to 0, and whenever you are asked question, you just have to substitute. Clear? Right? Now we'll do, we understood the question. I have drawn the figure, guys. Here this is again a ladder. I have just drawn it like this. Okay, so a person or a mechanic is going to move from here to here, let's say by a distance x. So you are asked what is the distance x, so that he will be, or the ladder will be just slipping. He is moving from the ground to top level. This much clear? Now to set this is smooth surface, this is a frictional surface which is having coefficient of friction as 0.6. This much clear. So again, it is at equilibrium. You are given the masses of ladder and mechanic as so. So static equilibrium means you can write F net is equal to 0 as the first point, right? So you can write Fx is equal to 0, Fy is equal to 0. Now what is Fx? What is the forces in x direction? That is N2, as well as you are having friction F. So you can write N2 is equal to F here, right? Similarly, what is the forces in the y direction? This is N1, and there are two forces downwards, which is 20 and 60J. That is, I can write it as 80G, or I can write it as G is taken as 10, it becomes 800. So N1 is equal to 800. Keep that as it is. Right, now the just ladder is about to slip, right? So that means what type of friction is that acting? The friction is limiting friction, which is mu into N1, right? This is the friction here, right? So mu into N1, I can write 0.6 into N1 has been calculated as 800. You will get it as 480. So the friction which is acting here is for 480 Newton. This much clear, right? So the next point which you can find regarding a static friction is torque is equal to 0, right? So again here the point of rotation we are going to assume from here, this point is where the rotation is going to happen. Let's say this point is A, right? So that means the torque due to N1 cancels out because it is along the axis of rotation, so it is not going to cause any rotation or any torque. Now similarly this friction, right, this friction, if I consider, this is also along the axis of rotation, so this friction is also not going to cause any torque. See, so when I decided the point of rotation to be A, this N1 and this F is causing no rotation, so that cancels off. Now then I can now write for torque due to N2. Now torque due to N2 is force, that is N2 into perpendicular distance from where? From here. So the perpendicular distance from here is this distance, right? That is this, let's say the ladder's length, I have not mentioned mine, the ladder is 10 centimeter, okay, so 10 meter. So this length will be 10 cos, let's say this angle is 37 degree, right? So this distance will be 10 cos 37 degree. So that is a perpendicular distance, right? So torque due to N1 is 0, torque due to F is equal to 0 friction. So torque N2 will be force, that is N2 into perpendicular distance is 10 cos 37 degree, right? Now see, this N2 is causing the motion in which direction? In anti-clockwise direction, right? So that means it is positive, so I will write it as positive. Now torque due to, similarly I have to find due to G, 20G, and torque due to 60G has to be measured. Now let's move on with the 20G. This 20G guy is the ladder center of mass acting, right? So center of mass is a distance. This air length is 10 centimeters, sorry, 10 meter means this length will be how much? 5, right? So the perpendicular distance is this distance, right? What is this distance? That is the perpendicular distance. So this vector, that is 5. Right? If this angle is for 37 degree, then this angle will be 53 degree. So this point, that is from A to, let's say, C. AC is 5. This is 5 now. So 5 cos 53 degree, right? And this force is causing a motion in this direction, right? So that is a clockwise direction, so I will take it as negative. So for 20G I will write it as minus 20G 5 cos 53 degree, right? Similarly for 60G it is also anti-clockwise now, so negative I can write it as negative. Force is 60G, right? What is the perpendicular distance from the axis of rotation? This distance I have to know, which is x, right? So x, right, and the perpendicular distance is this much, right? So x cos 53 degree, right? So here I will write this x cos 53 degree. Now these three torque forces, when I add, I will get the sum 0, right? So by calculation now you can find the x value, very easy. You just have to equate it and write cos 37 degree. If you don't know, it is 4 by 5, and cos 53 degree it is 3 by 5. Calculated, you will get x is equal to 9 meter.